Welcome to this week's Origins Colloquium. It's great to have UVA's new arrival, Stanley Baronet, giving the talk this week. Stanley just received his PhD this year from University of Nevada, Las Vegas, and I think we'll hear a lot about the work he did there on protoplanetary disks. He has two degrees. I learned bachelor's degrees, one in philosophy and one in computer science. So from UNLV and one philosophy from Hawaii. So, well, he's done a number of things that are very interesting advanced simulations of protoplanetary disks, and we look forward to hearing your new results. And well, to UVA.
Good job. Yeah, so today I'm going to talk about this kind of the bulk of my research, the scope of which goes from, as the title implies, from dust to planets, with a focus on dust-gas dynamics and radiation transport. There's a bit of an outline of the talk. I'll begin with some context, where I'll first unpack what we think we know about protoplanetary disk structure from a theoretical standpoint, and then broad strokes go over the many different processes involved in planet formation. And I'll pose a very key question that I've been trying to solve and will continue to solve throughout my fellowship here at UVA. And I'll give some of the answers that we've been seem to hope to have gotten so far with some of the methodology that we've used in trying to produce these multi-physics and ultimately multi-scale frameworks of protoplanetary disk models. And so what I want to emphasize is just the true number of scales involved in the planet formation process, starting from the protoplanetary disk scale, going all the way down to submicron sized dust grains, building up from there to centimeter, millimeter sized pebbles, kilometer sized planetesimals, and eventually forming fully formed terrestrial planets like the Earth. And as well, emphasize the various physical processes involved throughout this journey. And we begin with the protoplanetary disk structure environment where we expect planet formation to occur. And if we look at a vertical slice through the midplane of the protoplanetary disk, we find that the gas density tends to be stronger towards the SAR and less dense as you go further out. And it's within this mostly gaseous system that percent of the mass is occupied by these mostly silicate grains, which will evolve throughout different processes. And they're also under the influence of turbulence driven by the disk itself, the dynamics there, which can aid in transport. And the grains interact with the stellar radiation from the star, which peak in the ultraviolet and even X-ray, that will in turn set the temperature of the disk. So we expect hotter temperatures as you go closer, cooler as you go further out. And this variation in temperature throughout the disk will in turn produce various ice lines, for example, water or carbon monoxide, where various molecules will either sublimate or condense typically on the mantles of these grains. And so you expect to find a pebble disk settled toward the midplane here that will vary in composition as a function of radius throughout the disk. And it's these grains that are ultimately involved in this planet formation, which we can represent as a ladder, where the submicron sized grains must grow some 13 orders of magnitude or more to form these fully formed planets. And it begins at the bottom end with interactions, particle sticking interactions, where these submicron-sized grains will collide with one another and preferentially stick and form larger aggregates to eventually reach the level of pebbles, which are typically millimeter, centimeter size objects. And it's this growth of these solid bodies that actually interact with the gas. Specifically, if the gas has a density gradient in the vertical direction, and we expect the gas to be less dense as you go further up, that also reduces the pressure. And so if the grains grow in size, they actually are able to settle toward the midplane due to vertical gravity. They're no longer pressure supported. And so we expect them to settle to these thin sublayers at the midplane, where they will subsequently undergo radial drift. And the radial drift is due to radial pressure gradients in the disk, where if we find that the temperature in the disk tends to decrease radially outward, we find the pressure itself will decrease outward. This produces a pressure force, in this case, in the outward direction, radially outward direction, opposing the force of gravity. And so this pressure-supported gas actually rotates at a subcapillarian rate compared to the solid particles, the larger solid particles that are trying to orbit at the capillarian rate. And as a result, these solid particles feel a headwind from this slower moving gas, which steals angular momentum from them, causing them to drift radially inward toward the star. But conversely, if you have a local maxima, a pressure maxima on the disk, then the interior to that maxima or bump, the forces are reversed such that the radial pressure gradient is now inward toward the star. So now the gas is orbiting supercapillarianly in that region, giving the particles there a tailwind, which causes them to gain angular momentum and spiral outward toward the maxima. And so depending on where you're at in the disk, typically these solid particles are driven toward these pressure maxima, which act as traps or dust traps. And large campaigns from ALMA, which have observed the continuum emission from the thermal emission of the dust, we see the ubiquity of substructures that form these rings, and follow-up campaigns, for example, the MAPS campaign, which have looked at the molecular line emission of various molecules in the disks, seem to indicate a correspondence between these, where the presence of pressure bumps might be and where the dust tends to accumulate, especially if we look at these azimuthally integrated radial profiles of these tracers. We could see that the intensity of these emissions can spike, particularly around snow lines or transition lines of these various molecules. And although this theory was worked out 50 years ago, we're seeing now observationally the confirmation of these kind of processes going on. And so the next substantial rung in the ladder, in the planet formation ladder, is the planetesimals themselves, which are the precursors to planet formation. And the reason they're the next big jump is that when you get to be about a kilometer or tens of kilometers in size, you're sufficiently decoupled from the gas such that further interactions are mediated gravitationally. And through accretion processes, these planetesimals can accrete pebbles themselves and grow to form larger planetary bodies. And so so at one end on the pebble side, from micron-sized grains to pebbles, you have electrostatics dominating the interactions there. And at the larger end, you have gravitational forces mediating the interactions. And so the question is, how do you span this gap between pebbles and planetesimals? And this is, in fact, the main study of planetesimal formation. And if we actually zoom into that vertical sublayer at the midplane of the disk, and you simulate a system of gas and dust, in this case, zoomed in so much that we're in the co-moving frame of the disk, the star is going to be constantly to our left, and we initiate the simulation, you'll see that the dust, well, I'll turn my screen here so those in the room can see a little smoothly. The dust will start drifting inward, but they'll start to form these filaments due to a streaming instability. And it's these filamentary structures that form kind of traffic jam-like structures that exchange enough angular momentum with the gas that they kind of stall their inward radial drift. And these traffic jams will continue to collect upstream particles, creating a feedback loop where these filaments can then, again, resist that natural inward drift. And the color map shown here show that the brightest regions are where the dust reaches sufficiently high densities that they start to clump these particles and reach high enough densities to trigger self-gravitational collapse directly into these planetesimals. And so with this kind of context set, the key question that I'm investigating is, how do the complex coupled aerodynamic and thermodynamic feedback loops between gas, dust, and radiation affect protoplanetary disk structure, dust transport, and planetesimal formation? And so we go back to the evolution of these grains. We expect that there will be a distribution of dust sizes as a result of this grain evolution from micron-sized grains up to pebbles. And depending on their composition, which depends on their location in the disk, what molecules of sublimated or condensed onto them, you can produce a opacity profile. In this case, we will use the D-sharp composition, where you could see the effective absorption ability of this grain population as a function of frequency tends to increase with frequency. And so the more intense radiative energy from the star at the visible and higher wavelengths can be readily captured by this grain population. And furthermore, as we discussed, the evolving grains will begin to settle into the disk in combination with the gas density distribution. So we actually can model, in this case, 10 to 100 AU kind of axisymmetric meridional slice of a protoplanetary disk and see that the dust density is highest at the midplane and tends to taper off as you go further up away. And it's the presence of this dust that absorbs that stellar radiation and effectively sets the temperature of the disk. And so you could see in this companion panel on the side that, as I said, the increase in opacities due to these grains preferentially absorb the stellar radiation, which peaks in the visible and ultraviolet bands. And because of the dust density at the midplane becomes so optically thick there that it effectively keeps the temperatures quite low, on the order of tens of Kelvin. But if you go high enough in the disk atmosphere where the dust densities drop substantially, the grains that are present there are able to absorb the stellar energy and effectively set the temperature there above 100 Kelvin. So you have this sharp temperature difference depending on where you're vertically located the disk. And sure enough, this is consistent with recent EXO-ALMA surveys, which have used various molecular line tracers to probe different layers of protoplanetary disks and study the thermal broadening of those molecules at these layers to essentially try to create a three-dimensional picture of the temperature distribution in these protoplanetary disks. And this is important for planet formation theory, especially protoplanetary disk theory and dynamics, which have looked over the decades at a number of different disk instabilities or hydrodynamic instabilities. For example, the vertical shear instability, the VSI, which classically produces these very long vertically oriented corrugation modes or elevator modes where the gas will create these columns of almost like convection throughout the disk, making the midplane of the disk very turbulent, which is not preferable for planetesimal formation at that midplane. But the classical models usually make assumptions about the thermodynamics. For example, they assume isothermal profiles where essentially the gas can cool instantaneously, which is not accurate if you consider more realistic full radiation hydrodynamics, where now the opacity of the disk matters and affects the cooling times of the gas. And as a result, preliminary studies have started to show that the optically thick midplane becomes actually quiescent. It resists this, it damps the unstable modes of this vertical shear instability, and instead pushes the turbulence up away toward these higher layers, where by keeping the midplane quiescent, you can enhance, or it becomes more preferential for planetesimal formation, which we don't want too much turbulence driving diffusion, which acts against the concentration needed to form these planetesimals. But again, because of the temperature set by the interaction of these dust grains with the stellar radiation, we have these different ice lines, which again indicate where various molecules of sublimate or condense. And the differences in these compositions will actually change the opacity profiles. So again, we looked earlier at the D-sharp opacity, but that's for a particular composition fraction of water and various molecules. And so if you change that, depending on where you're in the disk, that'll change the opacity profiles, which in turn create opacity transitions throughout the disk. So we expect around these ice lines, or even, which would be of course interest to Jonathan Tan, the silicate sublimation line, where of course we expect that opacities transition very dramatically, very close to the star. That these opacity transitions will affect the temperature structures in those regions, which will in turn create radial pressure gradients, which we've discussed earlier. And these radial pressure gradients can actually affect the turbulence that's happening, for example, in the streaming instability in these regions. So we've looked at, in these streaming instability simulations, we varied the radial strength of the radial pressure gradient in these boxes to effectively simulate how close or far away you would be toward a pressure bump. So if the pressure gradient's weak, it would mimic what you would expect to find closer to pressure maxima, and a stronger pressure gradient would be found further away. And it turns out that as the pressure gradient decreases, the maximum densities reached by the streaming instability, which is what you want to form planetesimals, is enhanced. But if you increase the radial pressure gradient, you're further away from the pressure bump. The effect is you inject more energy into the system. And this added energy actually drives further turbulence, which is self-generated by the streaming instability itself, that it actually enhances dust diffusion, which acts against concentration. And so we actually expect planetesimal formation efficiency to decrease as the pressure gradient increases further away from these bumps. And
that's somewhat counterintuitive, is it? So with stronger streaming instability, the extra turbulence you generate damps out.
Yes.
So you're saying the streaming instability saturates?
Yeah, absolutely. Yes. Yeah. And I'll show some plots of this later on. But yes, the system will saturate itself. That's correct. So and the average, go ahead.
But surely then it's still stronger there to sort of reach the maximum value. I guess you're saying the saturation level is dependent on the pressure gradient.
That is correct. So the saturation level is dependent on the pressure gradient. What happens is that as you inject more energy into the system, because the stronger pressure gradient creates a larger headwind, right? So the primary mediating interaction between the dust and the gas is the relative velocity between the two. And so if you increase the pressure gradient, you increase the relative velocity, so you're injecting more energy into the system. That additional energy has to cascade somewhere. And so when you once the streaming instability saturates, you get this turbulent cascade. And if you inject more energy in the system, then it has to go somewhere. And so the smallest scales end up getting disrupted, where at the smallest scales is where you would expect to find the largest clumping. And so that diffusion actually ends up acting against the concentration that we want to form these planetesimals. Does that make sense?
I think so. Yeah.
Okay. Yeah. We could discuss more, and sure, I'd be happy to discuss more on this. But yeah, so you can actually study these simulations. We can actually measure various properties. For example, the turbulent alpha by measuring the Reynolds stress tensor of the gas itself directly. We can actually measure the dust diffusion by actually tracking. We can track every individual particle in the simulation and measure the diffusion coefficient of this population. And as a result, you can actually estimate the dust to gas height scale ratio, what we expect in the vertical sense, as a function of the radial pressure gradient. You can see you could form these scaling laws. And again, we're just discussing, the dust diffusion increases with radial pressure gradient. And this can be compared with observations where we looked at about 10 different substructures in a couple different disks, where these dust rings have a particular amount of their extended features. They have a little bit of diffusivity to them that must be accounted for by turbulence, because if there were no turbulence present, we'd expect these dust rings to be infinitesimally thin. And observers have already tried to model these by comparing the level of alpha turbulence in the disk against the presumed grain size population, or sometimes referred to as alpha over Stokes, of these features. And we find that in about half of these substructures, the streaming instability alone can account for the level of turbulence that's occurring in these features. So presumably the streaming instability is operating in these features and is producing the the extended nature of these dust rings. And then the other half of rings we looked at, the level of turbulence estimated by the observers is actually too strong to be solely accounted for by the streaming instability. So although the streaming instability may be present, it alone can't account for the level of turbulence in these features, and therefore other sources of turbulence, maybe the vertical shear instability or the things like that, might be driving this additional level of turbulence that is causing these features to be extended. Yeah, go ahead.
Super quick on the last plot.
Yeah, no problem.
Left to right, is that outer inner disk or inner outer disk?
Yeah. So it's actually strength of the radial pressure gradient. So if so, for a typical, if there's no pressure maxima present, then you actually need a pressure maximum. Because if you had if there are no pressure maxima present, then the gradient would actually be constant throughout the disk. So you wouldn't find any variation in pressure gradient. So the only reason you have, because this is the derivative of the pressure profile, right? The only reason you have changes in the gradient is if you have a local maxima in pressure profile. So you actually need a pressure bump present for this to change. And then to answer your question, so around the pressure bump, left would be closer to the bump, right would be further away from the bump, but it's actually symmetric in some sense. So going back to the video, you saw the dust tend to drift inwards to the left of the star, but that's because in that simulation the pressure gradient was outward. But you could imagine if you were interior to a pressure bump, the forces would be reversed. So actually the drift would be happening outward, and the gradient would be in the opposite direction. So in some sense, it's relative to where you are in the pressure around the pressure bump. Yeah, if that makes sense.
Thanks for clarity.
Yeah, no worries. Yeah. So to finish off, I'd like to kind of highlight the methodology we've been using to investigate this question, and we'll continue to do so, primarily using the Athena++ hydrodynamics code, which uses the finite volume method in that you decompose the system into kind of these equal-sized cells, finite volumes. And in particular, the benefit of this code is that it supports static or adaptive mesh refinement, which is shown here in this logo for the code, where as a result, you can increase locally the amount of resolution you want to capture the accuracy of the dynamics in those regions, while simultaneously allowing regions that aren't necessarily interested in to be at a coarser resolution. And so this produces an overall benefit in the computational performance of the code without unnecessarily having increased resolution in regions that aren't interested. And of course, the code supports high performance computing parallelization, and it's also open source with the repository and GitHub. And as a result, the community has contributed different physics modules to the code. In particular, of interest to the question I'm trying to answer is they've included dust modules, which either can model the dust as Lagrangian particles, which was in the video I was showing earlier and some of the work I've done already, or as a pressureless fluid, which has its own benefits, as I'll touch on in a moment. And finally, the multi-group radiation transport, which can allow us to do these radiation-hydrodynamic simulations with frequency dependence. And Athena++ isn't the only code that can model dust as either a fluid or particles. In fact, we've looked at 7 different codes that model the dust as either, you can see in the left group, dust fluids, or on the right, dust particles. Pluto being one of the other codes typically used in Europe that can do both dust fluids or dust particles. And we see that qualitatively, the evolutionary picture of the streaming instability for a particular set of parameters is in good agreement across all these codes and between dust implementations. Although if we zoom in, for example, on the border between these groups, we find that at a moderate resolution of about 512 squared, and in this case of dust particles, you only have about 1 particle per cell on average, that immediately you see a difference in the snapshot here of the dust density field, because the noise that is present here is due to the Poisson noise as a result of the interpolation needed to interpolate presence of the Lagrangian dust particles against this fixed Eulerian grid, which you do not see on the left side in the dust fluid, where essentially the dust, again, as a fluid, has a scalar value anywhere in the grid. But if you increase the number of particles that are present, which you could see here when we did for Pluto, by almost a factor of 10, that the mass resolution by these particles is increased, and analogous to smooth particle hydrodynamics, increasing the number of particles increases the spatial resolution. And so you could see this Poisson noise gets dampened to some extent and becomes more fluid-like as you increase the number of particles. And sure enough, if we look at the time evolution of, for example, the maximum density reached in the simulation, that by increasing the number of particles, it lowers the initial maximum densities closer toward what we see for the fluid code shown here by these solid lines as compared with the particle codes in these dotted lines. And in fact, at turbulent saturation, if we look at the cumulative distribution function of the dust densities, with the highest densities reached in the simulation in the bottom right tail here, we see a difference at lower resolutions between what dust fluids are able to capture and what Lagrangian particles are able to capture, although that the effect of increasing the number of particles present in the system tends to lower the, or I should say, bring the distribution somewhat closer to what we see in the dust fluids at this resolution, although it still differs anywhere from a factor of 2 or 3 at lower particle resolution versus maybe a 50% difference here as you increase the number of particles present. But if you go to higher grid resolutions and with the inclusion of additional particles, then we see in this time evolution plot in the bottom, this is a simple moving average actually of the maximum densities reached. All the codes begin to agree with one another a lot more closely. And in fact, if we look at the same distributions now, and we focus on the bottom panel, which take the average of these distributions for either dust particle implementations or dust fluid implementations, we see that there's a much better agreement at higher resolutions across all the codes. And this discrepancy between dust fluids and dust particles begin to go away, that were much more exacerbated at lower resolution. But because the dust particle distributions seem to already be converged with respect to resolution, at least for the shared probabilities that we see, then the biggest change is actually in the dust fluids as you go to higher resolutions. We note that any streaming instability simulations that use dust fluids may want to seriously consider the amount of resolution that they're using so that they don't underestimate perhaps the planetesimal formation efficiency that the streaming instability could provide. And those things.
These are single size models, aren't they? For
correct, monodispersed particles. That's correct. Yeah. So in these cases, there's no grain evolution, which I could touch on later, which is quite a difficult computational problem for Lagrangian particles. But you're right; these are monodispersed particles in this case. So moving on to the kind of last piece is the multigroup radiation transport. It uses what's known as the discrete coordinates method instead of alternative methods, which are often used as moment methods, which have their own limitations. For example, they tend to, because they treat the radiation field as another fluid, they actually tend to, as a result of their closure relationships for the radiation transport equation, will inadvertently cause beams to merge instead of crossing as they should physically do. They also suffer issues with properly casting shadows, and as a result of taking limits in how radiation transports as a function of optical depth, they're unable to properly model intermediate optical depths, which are of course important for the protoplanetary disk context. And the protoplanetary disk context being a non-relativistic context, the module also implicitly solves the time-dependent radiative-transfer equation, thereby avoiding any limitations to the time step due to the drastic difference in timescales between the speed of light and the sound speed, for example, in gas. And finally, it's frequency dependent, which is important for, again, looking at the frequency dependent grain opacities that we are interested in for this dust. And so you can divide the frequency piece up into various bands to kind of capture what's going on. And as I mentioned, it uses the discrete ordinates method, which essentially discretize. So you essentially solve the radiative transfer equation with emissivity and opacity source terms in the lab frame along what are known as discrete ordinates, represented by these n hat vectors in blue in this Cartesian grid cell here along different lines. And what we've done is added radial rays to properly capture stellar radiation from a point source at the origin of the system if you want to model the system using spherical coordinates. So this produces better accuracy there, which we've actually compared with typically benchmark codes, benchmark radiative transfer calculations using Monte Carlo codes, in particular RAD-MC3D. And if we look at various radial profiles along certain meridional latitudes of interest, for example, along the midplane with this transition layer region or well in the atmosphere, we see that with 64 bands, our framework can produce absolute relative differences between the two on the order of percent, better than 10%. But if you carefully optimize the number of frequency bands you have down to as few as 3 instead of 64, we find that the differences with Monte Carlo techniques may only double, but still less than 20%. But instead, you gain a factor of 10 in performance, essentially, by reducing the number of frequency bands or sets of equations you have to solve in the system. And similarly, if you tune the number of discrete ordinates that you want to capture the transport, this can aid in the goals of producing these multi-physics modules capturing gas, dust, and radiation to capture the multi-scale and multi-physics going on in the simulation, and maybe even eventually incorporate photochemistry or chemistry in general, as there is a module available in Athena++ for this. And again, this is all driven by connecting theory with observation and kind of tuning these models. And with that, I thank you for your attention, and I'm happy to answer any questions, go into any more details, or further discussion. Thank you.
Great, thank you very much. Time for questions and discussion.
So in Zoom, just raise your hands, or
Here, raise your hands. Right.
Yeah.
Hi, thanks for the nice overview on all the theoretical and numerical aspect of
Mhm.
a lot of that information.
Yeah.
Quick question about the Athena++ codes. Can they handle just one source of radiation that they can do, like from just the star, or can they have multiple sources of radiation, whether it's like a binary star or
Yeah.
a star in a cluster with a really strong external radiation field? Curious how that kind of gets folded in and how it affects the dynamics and
Yeah, absolutely.
dust gas.
So, yeah, there's actually a lot of potential applications for this framework. So the model we've shown here, it can kind of capture, in this case, because of the way we have the density profile set up,
Right.
more like a transition disk where you actually have a dust cavity in the inner model. But in principle, you can adjust, because what we do is we essentially inject radiation at the inner boundary. You can actually make that radiation time dependent. So in principle, you could model a binary system where you'd have variable luminosity, in this case, oscillatory, right? And I've begun working with some collaborators on trying to model how that might affect the protoplanetary disk structure.
Can you do a separate source, like I don't know, a protoplanet that's orbiting around, it generates radiation?
In principle, yes. So because the domain does not include the central source, right? We approximate what the source of radiation is along the boundaries. In principle, you can inject radiation from any direction you want. So if you wanted to capture, let's say, cosmic ray through the disk from some outside source, you could tune the boundaries. And again, because this is frequency dependent, you can say, okay, there's a source of radiation in this frequency band.
But what about a source in your domain that's orbiting around?
Again, so similarly, you could you wouldn't capture the let's say, you'd have to approximate the dynamics of that, right? So in the case of a binary system, right, you would have to kind of figure out ahead of time what the radiation exposed that the inner boundary would be for this oscillating binary source, right? So as the two stars pass through each other, we expect some kind of oscillatory radiation profile at the inner boundary. And then you could essentially program that into the boundary to mimic what it would be like. And you can make it angle dependent. So you can change it where, if you're above the disk, then you're going to experience that, let's say.
It sounds like you want to keep it on the boundary and not have sources in the domain.
That's currently how we're doing it right now. Yeah, because because there's already problems with modeling stars in hydrodynamic codes.
Sure.
That creates a whole host of other things. Not to mention, least of all, just because as we discussed the timescales involved, right? So especially if you're in spherical coordinates, right? As you get closer to the origin, you have a singularity, the grid gets smaller and smaller, the time step grinds to a halt. So you would essentially want to restrict your domain to regions of interest, right, and approximate as best as you can what the radiation field's doing there. But in principle, yes, you could do things like a binary star, how the radiation would be felt for the rest of this from that. Cosmic rays.
I think Ryan has an interest in external photo evaporation.
Oh, please, yeah. Go ahead.
Have there been models like that with just some external evaporation done in Athena plus?
There in Athena++, I'm not aware yet, at least in the protoplanetary disk context. There was a cosmic ray transport module before, much earlier in the code that I haven't played around with, and I'm not sure to what extent people have used that.
But what about photoionization?
Photoionization, yeah. So that has yet to be done, to my knowledge. And this is something that ILSA would like to do here, is because, like I said, the chemistry. There is a chemistry module, and is written by a professor at University of Texas El Paso, Munan Gong, who actually studies the ISM and was looking at photoionization, things like that. But as to my knowledge, in a protoplanetary disk context, it hasn't been done yet with Athena++. But go ahead.
It looks like Jonathan, just to comment on that, there was this paper by Zianpras where they
Alex,
have this external source that can form substructures from a shadowing effect.
Yes.
I don't know if that was Athena++.
No, he's using Pluto.
That's Pluto. Right.
It's Pluto. It's also using so Pluto uses a different type of radiation transport, which is one of these moment methods I talked about. So it actually uses, they call flux limited diffusion, right?
Yeah.
And which interestingly can not necessarily capture shadow casting properly.
But it's in test to see if.
Yeah, so I'm actually working with that group.
Yeah.
We're looking into doing a comparison study between these methods, between Pluto and Athena++ using either fluid flux limited diffusion, or in our case, discrete ordinates. And yeah, there's already, as Ryan's mentioning, they're looking into different dynamical effects on the disk due to things like shadow casting or misaligned disks. Xiangja Zhang is another person who's been doing this actually in Athena++, who's looked at, in the case of a misaligned inner disk, it'll actually cast a shadow along the outer disk, which have already been seen as these dark lanes in some observations, and he's trying to capture that. And this is all using Athena++, although his is actually not using any frequency dependence. So yeah, there's a lot to go. Go ahead.
Let's go to Ilsa.
Yeah, related to this topic. Very nice. Thank you for the presentation. So for the terms of like adding in the variable source of heating or radiation field or whatever, do you have to then worry about the time scales for like cooling or for the radiation field to subside? I guess is Athena++, are those timescales now too short? If you were to add like a tight binary in the center, like creating variable radiation fields, can you actually accurately capture the cooling or the reset? Same is true of the shadowing case. Like if you have something now, you're forcing your code to operate on like years, tens of years maybe. That's pretty short. What problems does that cause?
Yeah, so this goes back to the benefit of the slide here real quick of solving the radiation transport equation implicitly. So that actually avoids a lot of the time step issue. So actually the So what's happening so the main time step is the hydro time step. So that's going to be dependent on the resolution of the grid and everything like that. How the radiation gets transported, because it's solved implicitly, you don't have to worry about like, oh, I'm much closer to the star, and therefore the radiation's being transported faster or something like that. That really the only reason the radiation module would slow the code down is because it's solving it implicitly. If there's a large difference in the radiation field, then there could be more iterations needed to converge on a solution. So actually, this plot in the middle kind of shows an example of this. So what we did in some hydrostatic tests of this model that we're looking at is, as I mentioned, you inject the stellar radiation from the inner boundary. So at time equals 0, you start the simulation, and actually it's like a shield was lifted and the radiation starts entering the system and propagating through the disk. And so what you're looking at here in the vertical column is actually the total radiation energy density in the system. And it increases as time goes on, as essentially this front of energy passes through the system until you reach the light crossing time of the system, in this case, 100 AU or so. And there's this turnover. And then after that turnover, essentially the radiation field is saturated and there's not a lot going on. The code is actually slowest during these early phases. And that's because at every time step, you must implicitly solve the radiation field. And because the radiation field is changing so dramatically at every time step, there's more iterations needed to do that until you reach essentially radiative saturation, in which case now the radiation field is no longer, it's more or less stable. And then the number of iterative steps to solve the radiation field between those drops down to 1 or 2 or something like that. And so to go link this up with chemistry and things like that, as long as the overall, I'd say macroscopic changes in the radiation field aren't dramatic, the cost of the radiation modules is negligible, if that makes sense.
And you have radiation pressure?
You have radiation pressure, that is, yeah. So there is exchange of energy there and momentum between the radiation, which is actually missing from a lot of the other models. So in fact, Shangji's models, Shangji Zhang's models, which where I showed earlier with the vertical shearing instability, but also his current work looking at these misaligned disks, he's modeling the stellar radiation using just ray tracing as a kind of what we call kind of a hybrid method. The way we've done it here is self-consistent. So it's using the radiation transport module self-consistently throughout, which allows radiation pressure to be captured properly, both from an incoming radiation source, but also internally if there was some kind of local heating, which of course is important for things like vertical shear instability and so on. So does that answer your question also, or did I miss something?
It does. And I just wanted to, that was good. And I just wanted to add that Munan Gong is part of the Cosmic AI collaboration.
Perfect.
And so we're actually working with like integrating Munan Gong's network also into Rob Guard's magical network. So there's a lot of room for collaboration here. So excited you're here.
Yeah, I should mention some competing efforts on that front that I'm aware of, because I work with some of the group at Los Alamos National Laboratories. As you might have seen in the code comparison, they have here this LA Compass code, which stands for Los Alamos, Computational Astrophysics Suite. And this former, I should say former because they have a new code coming out, which I'll get to in a second. This code was private, and so there's no, it's not open source, and only people at Los Alamos could use it. But they have a new code now called Artemis, which is open source. It has a GitHub repo and everything, and it's becoming quite the formidable competitor code because it's essentially cannibalizing everything else. It's in fact got a rebound module included to do n-body dynamics. It's also doing its own radiative-transfer using a method implicit Monte Carlo, and it has dust fluids and things like that. And so it's trying to do similar efforts in combining all these physics and chemistry. And so I was at a talk recently where they threw all these things in, including chemistry and dust growth, because if you model the dust as a fluid, it lends itself to the Smoluchowski equation, which you can easily track now how the grain size distribution kind of evolves. So you can have a polydispersed population there. And they're trying to do grain chemistry. And one of the things they're doing, because actually the chemistry becomes the big bottleneck for the computation time steps, right? The reaction rates and things like that. And so to alleviate that, they will make the quote unquote chemical updates more sparse. So they maybe will update the chemistry every 10 or 100 orbital periods or something like that to avoid having to do this constantly at every time step. So there's different strategies to kind of mitigate where these bottlenecks can happen. So that would be something presumably, if we incorporated the chemistry into Athena++, it's not something we would need to update on every.
You don't need to update it.
Exactly. Right. So just, every tens or hundreds of orbits, there'd be a long calculation to get to update the chemical network. But otherwise, you kind of let the things go. I think you have a question. Yes. Sid?
But the grain growth was like in
Yeah.
the simulation, or was it like post processing that?
Oh, no, it's in the simulation.
In the simulation.
Yeah, so as far as on the Athena++ front, I have collaborators at the Center for Computational Astrophysics. There's a postdoc there, Thomas Feil, who actually formerly worked with, he's a PhD student of Till Bernstiel, and he, as part of his thesis, wrote it's called Tripod, which is a very efficient kind of dust evolution polydisperse model. And the reason why it's efficient is the word tri means he's only discretizing the grain size distribution into 3 bins, but you get fairly accurate results with that. And he's currently actively working on integrating Tripod with Athena++. As I mentioned earlier, there's a dust fluid module written by a researcher of, I think, mainland China now, Pinghui Huang. And so there's already the framework there to model the dust as a fluid with as many bins as you want. And so Thomas is trying to incorporate, again, involving the Smoluchowski equation through this tripod to get self-consistent grain evolution in the disk. Yeah.
So Daniel has a question.
Yeah, please, Daniel.
Hey Stanley, great talk. I think you
Thank
probably
you.
just answered my question, but yeah, I was wondering, like, since a size distribution for the dust can change the radiation field quite a bit, and so I was
Yes.
just, yeah, I guess maybe you just mentioned, but I guess is it easy or difficult to include different size distributions so that you can solve the radiation field properly and also evolve the dust to see this SI? Is that possible?
Yeah, so that's ongoing.
Right.
Whether I will get to it first or others is a matter of
I see.
debate. But yeah, you're absolutely right. Right. So as I mentioned, Thomas is working on evolving the grain size distribution. Right. One avenue of collaboration I could do with him is what you would do is you would pre-calculate in fact, all the work I've shown here, the opacities are pre-calculated. And you can see in our case, we used Till's D-Sharp opaque tool. So you give it a grain size distribution, you give it a composition, it'll produce a monochromatic opacity profile, right? And then you could tabulate that ahead of time. And so at any point in time during the Athena++ simulation, it assesses for a given frequency band, we'll take the monochromatic opacity and then compute things like the Rosalind mean and the Planck mean opacities,
I see.
drawing from this table, right? And so, as you mentioned, Daniel, yeah, if you have multiple dust bins, which essentially capture various portions of the distribution, you could pre-compute different opacity profiles for the different dust grain distributions, which is actually something I'm planning to do for sure as part of the fellowship here. Is one of the first things I'd like to do is just with 2 dust fluids capture a larger grain size that we expect to settle toward the midplane, and a more diffuse, smaller dust grain size distribution that would be well coupled with the gas. And so you're capturing the dust gas dynamics there. But then they would have their own separate opacity profiles, right? And then a further addition beyond that would be accounting for changes in the composition, right? So in principle, if the dust fluid is within on the ice line and the ices have sublimated, then you would, using a different composition, compute that opacity profile. And so self-consistently, you could have try to capture these opacity transitions that we expect in the disk. And in fact, Mario Floch in Germany has been doing this, especially near the dust sublimation radius, where they look at how the opacity changes in these radiation hydrodynamic simulations around that sublimation front. And they're able to robustly produce pressure bumps in that region, right where the opacity transition. So we expect to find similar things done, although to my knowledge, it hasn't been done yet self-consistently in hydrocode further out with these other ice lines where like where the water is or carbon monoxide, things like that. Does that answer your question, Daniel? Or
Yeah, yeah.
But let me follow up a little bit.
Yeah.
So, for example, how well can you predict how much dust is in the upper layer of the disk? Shouldn't it all just grow and settle down? What is the the vertical metallicity profile?
Yeah.
The abundance profile that becomes stabilized, or is that not even modeled or resolved?
No, there is. So as I mentioned, like turbulence is pretty ubiquitous and robust in the disk. And so if there were no turbulence, then yes, essentially all the dust would settle to the midplane and you get an infinitely thin layer. But as I've shown already, the interaction of the dust with the gas itself produces either in the streaming instability case, which is typically in the radial direction, but the streaming instability is actually part of a larger class of things called resonant drag instabilities that groups like Jonathan Squire and Phil Hawkins have looked at, which can actually occur in other contexts, for example, in vertical settling. So you can actually get unstable interactions between gas and dust from the settling of the dust itself toward the midplane, which can become its own source of turbulence. And so the point is that you have all these sources of turbulence. The disk is never quiescent, and that's stirring the dust up,
But don't
continually keeping a population up.
don't you have to have lots of size bins for your particles? Or
Yeah.
So in the particle approach, don't you have to have many size bins to accurately follow this?
Oh, of course, yeah. So depending on what you're trying to study, yeah, you would need a lot more size bins. But one of the things that Till's group has studied with their I think it's DustPy that's trying to model is, and this is still ongoing research. There's no I think there's room for further investigation on what the values are for these parameters, being things like what's known as the fragmentation velocities and things like that, right? So things like the fragmentation. Let me. I have a slide over here. Let me get.
Yeah. So in the limit though, where just trying to think why it stabilizes, it's pretty dense.
Grains grow, they settle.
Well, so but I mean, it's not a hard arrow like the arrow of time or something where you're only going to form larger bodies, right? There are processes that will destroy these bodies and produce. Yeah. So I mean, as I'm showing here in this plot here, you have things like the bouncing barrier, fragmentation barrier, which create problems for forming planetesimals, but they're also the source of keeping the distribution from becoming too top heavy, essentially, over time. And so and like I mentioned, these are the parameters of things like the collisional velocities of these particles. They're I wouldn't say they're conclusively constrained. And so these dust evolution models coming from Till's group, for example, that look at how the dust size distribution evolves with time, those assumptions will change the timescales of those of those distributions, right? So how quickly you form larger bodies and then essentially eat up all the smaller grains depends on things like the collisional velocities of the how efficiently that is. Another one that I didn't mention is a bouncing barrier, and I'm aware of active research now going on regarding the efficiency of how these particles stick with one another, right? So classically, there was tables produced from laboratory experiments looking at the surface free energy of grains with various ices on them. But this was done assuming certain properties of water on the surface on Earth at 1 atmosphere and so on. And so there's groups now looking at molecular dynamic simulations, trying to compute more accurate surface-free energies of these grain surfaces in the protoplanetary disk environment. And some of the results may show that if you have these icy grains, they actually might be less efficient at sticking with one another than previously thought. And so this lends itself to the bouncing barrier. So it's not always the case that collisions or interactions always lead to dust.
Well, maybe that's a good test problem to
Yeah.
get a vertical dust profile.
Correct.
Because
I think
Yeah.
that's constrained by the chemical models in the upper disks as well. You need to.
surely the dust surface impacts the chemistry, I think.
Oh, for sure, I would imagine.
Okay, any other questions for Stanley? Okay, if not, let's thank Stanley again for a great talk and discussion.